Non c'è nessuno connesso. Siamo solo noi due. Però, siccome sto registrando, non so se mi tocca lo stesso farla in inglese. Se poi qualcuno la vede dopo. Vabbè, per me è uguale, cioè, però decidete voi. Va bene. Va bene. Vabbè, a meno che non si collega qualcuno. Io cerco di tenere qui la chat aperta. E così vediamo un attimo. Adesso siamo qua. Allora. Perfetto. Non funziona niente. Perfetto. Allora, la volta scorsa eravamo arrivati a vedere un po' di machine learning. Abbiamo fatto anche qualche esempio, diciamo, su Matlab, anche per farvi vedere un po' che effettivamente il problema non è tanto quello di creare un classificatore tra la vasta gamma di classificatori che esistono in letteratura, quanto piuttosto quello di decidere le feature caratteristiche che rappresentano il vostro fenomeno. Cioè, se voi state osservando un fenomeno con qualche sensore, eccetera, dovete prima di tutto diciamo, abbattere, diciamo così, la dimensione del vostro dataset cercando di estrarre le feature più caratteristiche dai vostri segnali, dalle vostre immagini, dai vostri video, in modo tale da non dare tutto il dataset così com'è in ingresso al classificatore, ma darne una sua rappresentazione in uno spazio dimensionalmente più piccolo, ma più ricco di informazioni. Quindi, nell'esempio dell'altra volta, visto che non ci avevamo, un esempio proprio scemo, parlato di, diciamo, predire se sta piovendo oppure non sta piovendo o sta per piovere. È inutile, diciamo, abbiamo la rappresentazione da sensori vari, eccetera. È inutile dare in ingresso a un classificatore, per esempio, un dato sul tempo, che ora è al classificatore, perché è un dato che non serve fondamentalmente a niente. Magari, oppure sulla temperatura esterna. Non sono dati significativi, piuttosto il dato, diciamo, un andamento di umidità, oppure un andamento della pressione, possono essere più significativi e queste sono le feature che poi diamo in ingresso al classificatore. Quindi l'ideale è individuare i parametri caratteristici del nostro problema per poi dare l'ingresso al classificatore. Possiamo decidere di dare l'intero segnale, però è più conveniente dare una rappresentazione del segnale. Per esempio, nel caso che avevamo visto riguardo l'analisi termografica da step heating thermography, avevamo visto che piuttosto che dare tutto un segnale, davamo una rappresentazione attraverso un'espressione analitica del segnale, quindi espressione analitica in 3 parametri, che sono derivati da un fit nei minimi quadrati. Questi 3 parametri che caratterizzano l'intera evoluzione del segnale sono le 3 feature e su queste andiamo a fare la classificazione. Questa è l'idea. Ok. Let's switch to English. So the basic idea is that in machine learning, instead of making something, a computer that is programmed to create some output and receive the program itself and the data, in machine learning, you try to understand your program, your code, you think that you want to use for modeling your process, giving data and the output, so and the expected output. And okay, that's the difference between supervised and unsupervised learning, where for supervised learning, you also have labels, so you get some examples in your training set, and you can make some training giving to your machine learning algorithm both the input data and the expected output that you want from your, let's say, classifier, but also from your regressor. Or in unsupervised learning, completely different. You don't have labels, so this is much more related to a process of data discovery, knowledge discovery, where you get your input data and then you cluster it to try to get some information from your input data. And then you use your machine learning algorithm on new data that are from a test set, for example, and get the expected labels or the cluster ID if you don't have the labels. So now we are focusing on supervised learning instead of unsupervised learning. So we see in the last lecture unsupervised learning. Now we are working with supervised learning. So we have our training set with both input and expected outputs. Then you can train your model, and then you can apply this model to new training data and make a prediction of your input of your new test data, and get from this prediction the estimation of what you are expecting. For example, in our classification, if there's a defect or the class of your defect, surface defect, input, in-depth defect. Now, this is another panel that more or less you should have already seen in the previous lectures, because here we get the differences between classification for an image in a computer vision task, then classification and localization, or object detection, where you want, for example, to identify the position of the bounding box of a specific object with some semantics, let's say the duck, the dog, the cat. Or you want to make instance segmentation, and this is semantic segmentation is our problem, where we want to classify every single pixel of the map. So this is a no-free lunch theorem that says us that there's a single classifier that works best for all your data. So maybe there's some classifier that works better for some input data, other that are better for other test data. So in any case, we make some approximations on your model, so you get an approximation of the reality of the actual physical phenomena that you are monitoring. That's the point of this theorem. And as for the evaluation, where we can derive accuracy, precision, recall, even for training, but for testing are much more significant, because in test you want to understand which is your accuracy on something that you had never gave as input to your network, to your structure, to your model. And then at the end of the story, say, okay, I'm able to classify or make a regression of the input of new inputs in terms of generalization. And this is the use case that we were looking in the past lecture for machine learning algorithm, and we have already trained some models for inspecting this plate of glass fiber and fused polymer. Now, this lecture is more focused on deep learning. So the first thing to understand is the difference between machine learning and deep learning. In machine learning, there's an important point that is up to you. So you should define the features, the best features that are able to describe your problem. And you are the expert of the domain, and you should have the whole knowledge about your case use case. And probably you're able to detect the best features and then to use it for feeding a classifier, and then train the best model to solve your classification problem, to get the best predictions. So of course there's a bias, let's say, that depends on you. That depends on your ability to pick the best features. Maybe you are not able to pick the best feature to choose it. In deep learning, there's a difference. So even features are automatically selected from your network. So that's the point, that's the difference. So your training data are not used only for training your classifier, but also to train something that is the architecture that you will design for extract the best features that hopefully works better than the others for your specific problem. So it's completely driven by your data. And maybe you can also have other features that are not, let's say, so straightforward to detect. Maybe you can find other correspondence or other correlations between features that are not so straightforward to find in your problem. In deep learning, this process of extracting features has an hierarchical sequence of filters. So typically you start from something, you create an architecture. That means that you are selecting some filters that are empty, fundamentally. And then with your training set, you will tune your filters to get the best representation of your input. So this is made for the first image, and then for any new representation that you get out from your filter bank, from your layer of filters. So you get several layers of filters that works on a newer representation of your input data. You first, for example, for an image, you just have the input image, then the first layer that typically is trained, and at the end of the training, get some low-level feature like edges, I don't know, the regional high contrast. So it's able to detect something at the first step. Then you get a new representation. For example, from this image, you get this first representation of the corners of the edges of your image, and then this new representation is the input of another set of filters that is creating a new representation of higher level. And then at the end of your network, you get the representation of the highest level. And then this is the new feature vector, let's say, that could be suitable to feed a classifier. So you start from low-level representations to the highest one, and then the highest representation, the representation of the highest level, is the feature vector that is proposed as input to your classifier. And okay, so why is this useful? Because you can use deep learning for without any knowledge of your domain. Well, actually, it should be preferable to have some knowledge of your domain, because maybe you want to explain your results and then go within your network and say, okay, which kind of filter is working for the specific image. And maybe you know that is an edge extractor. Maybe you know that in your specific application, you will enhance your edges to make this filter work even better with input images. So there's always the need for some explication of your filters within the network. So just some, there's another important aspect which is related to representational power. So we have seen something about the neural networks in the past lecture. And we already know that neural network can be used for modeling even something that is not linear. Okay. And a neural network, as in the previous lecture, was defined as something that has an input set of neurons, then there's a hidden layer, and then the output layer. So we just have 3 layers where the input is receiving signals, then the hidden neurons are processing your signals in a nonlinear way. So with a linear combination of weights and a bias, and then with the nonlinearity that is given by an activation function on your on every neuron. And then this is the input for your output layer that is making the final classification. So the output of each neuron is somehow related to the probability of your input to belong to some classes of some of your classes. And why we want to use a deeper neural network? So instead, as in neural network, in artificial neural network, as the ones of the previous lecture, we have just 3 layers. Why we need to improve the number of layers? Because we want this hierarchical representation of the feature. So we want to go step by step from something that has a low level representation to something that has a higher level representation. And there are many frameworks where you can develop your deep learning. For example, I use PyTorch, that is Python-based, but in this lecture we see something with Matlab that maybe is more familiar for you, and surely it's much easier to understand than PyTorch. But there are also, I don't know, Keras, TensorFlow, and many other frameworks where you can develop your architecture, your models. So let's start with neural networks. The same that we have seen in our previous lecture. So let's start with this use case, the handwritten digit recognition. So we had 10 digits from 0 to 9, and we want to recognize these digits that are in the form of a 16 by 16 square image. Okay, so you can reshape your input, for example, reading along the rows, in a vector, let's say in a one-dimensional vector of 256 elements. Okay, so these entries are the entries for your neural network, and your neural network should have at the end, at the output layer, 10 different neurons, and each neuron returns the probability that your input image belongs, for example, to a specific class. In that case, you get that, I don't know, 0.7 means that this is true. Okay. So mathematical representation should be a function. This is your model, a function that has as input a vector of 256 entries, and then returns a vector of 10 entries, nothing more than this. And if you look at the third entry, for example, this should be the maximum among all the entries of your vectors, so suggesting you that probably this is a 2, with a probability that is equal to 0.7, 70% in our example. How it works. So you take all your inputs, then you get some weighting matrix, and then you sum up a bias. This is made for every neuron that you get in your 18 e 30. And then you, with an activation function, you produce your output. This is made for every single neuron. When you get the final architecture made of your input hidden layer, output, you get that your input layers has this form here, while your output layer has this form. So the output produces the vector y, that is the vector of the probabilities of the 10 classes. Then, how many, so let's say that we are neglecting the input layers, okay? So just hidden output. You get 6 neurons, of course. So the first one are 4 neurons, and each neuron, since this is a fully connected network, takes 3 inputs, okay? And then you get 12 weights and 4 biases. And then the same for the output layer, you get 1, 2, 3, 4 by 2 weights, so for a total number of 20 weights, and then 2 biases, because you get 2 neurons, okay, in this specific probe. So you get 26 learnable parameters. So for this very, very easy network. But then you can increase the number of hidden layers like this, and this is known as a multi-layer perceptron, which can be also represented in matrix form once you get that all the points in your network is linked to any other following neuron of your network. For example, so this is just an example that you can see here, where you get for each arrow there's a weight, and then there's a bias here in this green square. You can have your summation of inputs till we get the final output as passed through a sigmoid function, which has this formulation. This is the activation function that is typically used to, let's say, squash your values into something that has a boundary. Because if you, for example, have here 4, and then you propagate this 4 along your network, maybe at the end of your network, this could be 4,000. So instead, you use some activation function to take it bounded between some limit, in this case from 0 to 1, because the domain can be whatever, but the output function is bounded between 0 and 1. And then if you create more and more layers, of course, then you can increase your complexity. But in any case, you can represent it in a matrix form, because the inputs can be multiplied by a weight matrix. This is the matrix product. And then a summation of, for every single element of the output here, by the terms of a bias vector, that are the bias of all the neurons that you get at this level, let's say. Then this level has this other, let's say, function. At the end, your y, the output, can be represented as a function of any single layer, where the input of, let's say, the health layer are the output of the previous one. Then you can create a chain of your model. Typically, instead of using just at the end of this layer, so here you can get some measure up at the end of your activation function, let's say 0.9, 0.7, 0.2. So instead of as you want, it's the output, the probability measure of of your input, so belonging to some class of your training set, or your test set as well, you need to normalize everything. So you typically has a softmax layer where the input of this is the last layer of your architecture. This is typically done for classification problem. At the end, you get exponential function. And so, for example, 3, the exponential of 3, so 22.7, 0.05, and so on. And then you sum up all the elements that you get in your final layer in order to make a normalization. Now, these outputs has sum equal to 1. So this output sum to 1. This means that this is an actual probability of your for your final layer. So what I presented here is just a softmax layer. So the summation of all these terms is equal to 1. So this has the actual meaning of a probability. Now, how many hidden neurons can we have in a multi-layer perceptron network? Of course, as long as you increase the number of hidden neurons, you will get, you can improve your representation, even including some non-linearities. So have something that is completely perfect here, for example, with 20 neurons. But maybe you can have overfitting. So as usual, there's a balance, something that is a trade-off that you will find while selecting the number of your hidden neurons and hidden layers. So the sigmoid functions are not the only function that you can use for your activation. So this is a sigmoid that we have seen before, that for any neuron you get something, some activation that, first of all, introduce the nonlinearity to make you able to characterize something that is as a nonlinear behavior, but also to take your outputs bounded between 0 and 1, just to have everything somehow bounded. So what's the problem here? That this is of course a nonlinear function and can make your training very slow. So instead of using sigmoid functions that, well, I'll typically use more for regression problems, we can use an hyperbolic tangent function. So with this formulation that is somehow very similar, but there's a region of linearity across 0. And also in this case, you can bound your output between -1 and 1. In, I can say, 99.9% of your networks, you will find this rectified linear unit, which is just a threshold function. So an activation function that, of course, is a nonlinear function. So if your output is negative, the neuron will not be activated. So your output will be 0. If your output is higher than 1, then 0 is positive, you will get the output as the input. Okay, so this is just a thresholding function. And why we typically use this function? Because this is a good trade-off for training the networks. So when you need to train something that has very high number of learnable parameters, it's better to use rectified linear unit activation function, because it's something that for an alpha is linear and then is a threshold. So you can, it's much easier to train a network with this activation function. But there's a problem also in this case, and in some cases, not too many actually, there's a leaky rectified linear unit activation function where you don't have perfectly zero for negative inputs. You get something with a very low slope. This is just for not having zero propagating your network, but something that is close to zero, but not equal to zero. And in the regression problem, you can use a linear function as the activation, okay? Where, of course, it's not, the output is, in this case, is equal to the input, but you can select your parameter C, the slope of your activation function. These are typically used for regression problems. And okay, so in any case, even if we have never talked about the architectures, I think that it is almost clear to you that once you define something, some sequence of filters, and then some fully connected network or any other thing you can put in your architecture, everything is initialized with random weights, random biases, random kernels, everything is random. So you need to train, you have to give your training set that is labeled, because we are in supervised learning. And then somehow you should be able to tune your parameters and get the best weights, the best biases, the best kernels that are able to reduce a loss function, okay? That's a kind of optimization problem. So in our very easy problem of the multi-perceptron layer network, our parameters, theta, are the matrix of weights for each layer and the vector of biases for each layer. So your problem is to find the optimum of your network parameter, given a cost function, something that we should make optimum. And once you get your optimization, your loss function, then of course you will get the best parameters and you have all your network, multi-layer perceptron network trained. Okay. So before training, typically there's a normalization of the inputs. I've already discussed about it in the previous lecture. So instead of taking your input and give as it to your network, maybe it's better to get a normalization, to bound your input between something that has a constant dynamic range. Because probably if you get that one signal, let's say, is of 1,000 in value, and then the other one is of 1 of the unit, about the unity in for another feature, maybe the comparison of these features is not fair. Okay, and of course your model should be trained more from the inputs that have a higher magnitude. Okay, so maybe it's better to get everything normalized. Actually, your network should be able to contrast this problem, but and that's the truth. But it requires more time for training. Okay, so because the network needs to understand that you'll somehow normalize the inputs to get comparable inputs in your network. So we can take it for free and give pre-processed data to the network, where pre-processing means create something that is normalized, so that the dynamic range is bounded, for example, between 0 and 1, and scaled, And the standard deviation is equal to 1 for each dimension of your feature space. And okay, so as I told you before, we should optimize the cost function. So we should define our function that is, of course, a function of the model parameters. This L theta function. How we can define it? For example, this could be, let's say, in a regression problem, the square residuals that you get from your prediction and the expected value that you get in your training set for a regression problem. Okay, you expected 1, you get 0.9, your residual is 0.1, the square is 0.01, and then this term is your cost, your error. Of course, this is just for one value, but if you get thousands or millions of input data, it should be the summation of all these errors. And of course, you can define for any input, let's say that you get a training set of n images, you can define your loss as a summation of the losses computed for any image. But which function can we use for a regression problem? For example, residuals could be a good solution. In case of classification problems, typically the cross entropy function is used. Okay, so you define this cost with this formulation where you get some ground truth labels. So these are categorical, class 4, let's say. So these are the ground truth labels. So what you expect from your input. So for a given instance of your inputs, xi, you will get that the output should be class 4, let's say. So this is class 4, a number 4. And then here you get the predicted labels. So instead of, for example, make a prediction of class 4, you get a prediction of class 3. In that case, you are making some mistake and your cost will be increased. You will compute it for any classes and for any of your input data. So this is the formulation. Now, for regression, as I said, you can define, for example, the mean square error. So the mean, the ground truth. So because you are working with something that with some data set, training set that is labeled, because we are in supervised learning. So you have your ground truths, and that's our case where our ground truths is the map blue everywhere with the circles colored according to the class of the defect. Okay. And now, for regression is something different. For example, mean square error can work fine for our problem. And also in this case, you get this is the actual value xy, ya minus this y hat. That means that is the predictive value from your model with the specific parameters that are defined in this theta. Okay. Once you are training, you are making a loop, and you are trying to optimize. You are trying to optimize these L functions, this L function, with the parameters of your model that are defined in your theta. Okay. How we can do that? So there are many ways for doing that. So typically, in deep learning algorithms use the gradient descendant algorithm. Okay, so you start, for example, taking your model parameters, let's say in this point. So this is the start. So of course, here we are making something that is easy, just with one model parameter, and then the cost function is this shape with just one minimum. So the best, the optimum of the cost function, of course, is the minimum of this curve. So we start here and we follow the direction of the gradient, but in a descending way. So this is the gradient, the slope of this compute, of course, in this point. Instead of, so from the left to the right, you will get an increasing gradient. So we want to move to the minimum, and so we are following the gradient descendant. Okay, so at the next iteration, you will use the parameters of your model that are able to make this gradient lower. So this function lower. So you are using the negative slope of your gradient. What's the problem? And this is what you get. So we are, let's say, flowing till we get a global minimum of your loss function. So you update your parameters in that way, where you get that your new parameters are equal to the parameters at the previous step minus an alpha term that is known as the learning rate multiplied by your gradient, okay, computed at the previous step of the parameters. So this is how we update the parameters typically. So this alpha is very important. This is a learning rate. That means how fast you can estimate your parameters. As you can imagine, this should be not too high, but not too slow, because if too slow, you will never reach the minimum. But if it's too high, you can make some oscillation around your minimum without finding it. We'll see now this point. There's another point that in any case, so your cost function has a shape with many minima. So you don't have just one minimum, global minimum for all the function, but maybe you can get many minima that are local and just one global minimum. So if you, for example, start here, your processing and say, okay, I'm following the gradient descendant, yeah, then you can fall in this local minimum that is different from the global one. Okay, depending on where you start your learning, which is the random assignment that you get with your input parameters, your theta parameters at the step 0. So, and there's no algorithm that is able to guarantee you that you will find the global minimum. Okay, and there's when you make multiple training of the same network, but changing the seed of your random sources, you can get different networks. So you will not find the same parameters. You will, let's say, arrive in different optimized parameters for your network. There's another point that, well, actually you can say, okay, when I make my my estimation of the loss, I get my input and then some trial of the theta parameters, and then let's go in a feed-forward process, compute the output y, depending on the input. That's it. And then estimate the cost function and try to optimize it. But actually, everything is made in a reverse order. So we start from the output to the input, and then for any, when you go from the last layer to the previous one, you define the alteration of your, the variation of your cost function for that specific layer, try to optimize it. Then you go back and try to optimize the other layer. So this is a process of backpropagation. So I don't want to waste more time on that. So there's a lot of theory behind this panel. So it's more important to understand how we can optimize the loss function, because as I told you before, there are many ways to make some training. Before, I mean, in the past lecture. So, for example, you can define a training set and a validation set between your training. When you use your training set maybe can be made of, I don't know, 10 millions of images, let's say. Instead of using the 10 million of images as a whole and giving them to the network, it's much more efficient for sure, but also it's better for the final training to divide it in mini batches. So you get 10 millions of images and you create some groups, lots of groups of, let's say, 64 images. And you train with this mini batch your network. So the first 64 images are given to your network and start training it and make the best optimization for only these 64 images. Then you have other 64 images, and then you tune your parameters till you get all the 10 million images. When you reach the whole data set, you complete an epoch. And then at this point, you compute your validation. Okay. When you compute the validation, you can state whether or not it's time to finish your training, for example, with some early stopping technique to avoid overfitting, and now we will see something about this. Or you can go on with the epoch and then train again. So shuffle the mini batches, and then again, 64 by 64 by 64, you can give these 64 images to your network. Why we use it? Because, let me see. Okay, I will talk about this later. But why you use mini batches? Because for any mini batch, you have, let's say, a different network. And we will see it because this is a way of regulation for your network. Typically, when we work with dropout, but we will see in 10 minutes this point. And there's another problem. So we said that we want to optimize our cost function. So if the gradient is not too high, maybe your movement, let's say that we have this ball that is moving on this shape to reach the minimum. Okay, maybe your movement is not too fast to get the convergence in, let's say, a good number of epochs. So you need many epochs to get the convergence. And how we can solve this problem? Adding, for example, the momentum. So let's say that instead of, once you get this point, that is a local minimum, so because here you get that your function is going deeper than this point. So you are considering some momentum, so some information about the previous steps of your training, so that you will not stop here, but you will follow, you will keep going with your optimization till we get, for example, at the next step, that this point is here. And then you will have that your negative of gradient will suggest you to go back here, but you get information about your previous step, that is the momentum, that is saying us, try to move farther on the right, in this case, to find some other minimum here in this region. Okay, so this is named the gradient descendant with momentum. So that's how we tune our parameters, typically with the gradient descendant. So that's what we have seen before. with the momentum, we add these beta parameters. So here we get that this momentum that you see here is equal to beta multiplied by this momentum at the previous step, plus your learning rate multiplied by the gradient at the previous rate. And then you can use you can how can I say, let me see, update, so your term here. So your update is not only this term that you get here, alpha multiplied by the gradient, of course, with the minus here, because we are in gradient ascendant. But you get also another parameter depending from beta that is giving information about the previous steps of your optimization, okay? At time t equal t minus 1, at the previous step. You can also include this update term, this beta, into the formulation of into the argument of your cost function. In this case, you get an ester of accelerated momentum. So just to speed up also your training. And there's another way. So these names that you see here can be imposed in PyTorch, in Matlab, in any framework you want to use. So you just have the idea that there are many ways to perform your optimization with the stochastic gradient descendant, with the ADAM, that is the adaptive momentum estimation optimization technique, where here you get the weighted average of the past gradients, as we see before, and then there's the weighted average of the past squared gradients. So you are adding another parameters, this beta 2, that typically 0.9, 0.999, or this epsilon, that is this other term that you see here in your update. Okay, so you just, I just want you to focus your attention that there are many ways to perform your optimization. For example, typically I use this ADAM optimization, and we will see also something when we move to Matlab to show you some example. So these are this is an animation that show you how the optimization can converge to the global minimum of the cost function. Okay. For example, here you can see that blue and black are working better than the other. For example, the stochastic gradient descendant is the slowest among all the procedure that you get for the optimization of your cost function. Now, that's the point of the learning rate. So the alpha term. If it is too small, maybe you will not reach your optimum of the cost function. If it is too large, you can oscillate around, and again, you cannot converge on the best cost function to the optimization of cost function. So how we can choose that? For example, if we, so this is a typical graph that we also seen in the past lecture. So when you are training, so you are evolving your network. So this is the epoch of your training. So at the first iteration, you start with some loss that is high. And then once you are getting more and more iterations in your process for your convergence, you will get that your loss is going to decrease. Or if you have an high learning rate, this could also increase. And if you get that you get, for example, a low learning rate, you will get the convergence as for a good learning rate, but with a higher number of epochs. So this means that your training will take, I don't know, 1 week instead of 2 hours. if you are using an high learning rate, you probably will get for the first epoch something that has a very good slope, so you are going to converge, let's say, fastly. But then once the epoch increases, you find a kind of plateau, and you are not able to converge to the best optimization. A good learning rate is something that is in the middle between a low learning rate and high learning rate. So you want to get this slope as high as possible in modulus, but not too high, but not too low, because you want to converge in the lowest number of epochs for sure for your training. So we can also schedule the learning rate. So instead of using just one learning rate for all the iterations, we can start, for example, with an high learning rate for the first epochs, and then start making this learning rate lower. So this means that your network, once you get your training for the first epochs, for the first examples that you are giving to your network, is going to learn fastly your process, but then is not using a learning rate too high to just to make a kind of fine tuning of the parameters for the last layers for the last epochs of your training. And you can make the first thing to do is the annealing. So there are many approaches. For example, you can reduce the learning rate. So you can say, okay, every 5 epochs have the learning rate, and this is a procedure. Or you can use some function, for example, a cosine function or an exponential function. So for the first, you multiply everything by the exponential function, and for the first epochs, you will get that your learning rate is high, and then is exponentially decreasing for, let's say, the other 30, 40, 50 epochs, okay, of your training. Then there's also a warm-up that is not typically used, actually, that you start increasing here your training, your learning rate, and then you go down with some cosine function, for example. So you are just gradually increasing your learning rate, just not to say to the network, okay, start with the highest learning rate you can, and then maybe you can get some problem. In this case, you are warming up your training, but actually it's not typically used in actual training. Now, regularization. So the problem of overfitting is something that I think is clear for you. So so if your model is not too complex, you are not able to use your model to make a good prediction, okay? And this is the problem of underfitting. So your training is not able to make this error minimum, okay? And if you are making something that is too complex, it's completely the opposite. So your training is perfect, you are getting the best results in training, but once you use the same model for testing, you get an accuracy that is very low. This means that your model is too in love with your training set, and is not able to generalize to everything that would be passed in as input for the test. Okay, so, and that's the point. So you're making this error in training very, very low, but when you get the validation, so you are validating your network on something that is new, your error is not comparable to your training. So this means that this network is too complex, and this network would make good predictions only on inputs of the training set. It's not able to generalize. And so, for example, here in the first square is underfitting. This is a good compromise. So it's not perfect in training. So there's a cross on the side of the curve. This is overfitting. So if you get something here because of noise, you will get a not so good prediction of your data. And for preventing this problem, for example, we can use a regularization term. This is, for example, an L2-way decay. So these are model parameters. These are numbers. So this lambda is something that is multiplied by your parameter, by the values of your parameters. So you are increasing the cost function by a term that is directly dependent on your parameters. Okay. So this means that if your weights are too high, let's say, you are going to penalize these weights because your cost function should be higher than the cost function that you get without any regularization. Okay. So you are somehow make a penalty for those weights that are very large in values. So you're saying to your network that in your cost definition, you also have something that is related to the magnitude of the parameters of the model themselves. There's also the one-way decay, but actually is not so used, or there's also a combination of both the way decay regularization. So this is known as the elastic neck regularization, but typically regularization is made by this L2-way decay. So for example, here, if this lambda term is very low, you are making probably nothing, and your model is going to overfit. If you are defining this lambda value equal to 0.1, you will get that this separation here in your feature space is smoother. This means that maybe you are making the best compromise. You are making, you are preventing overfitting. Okay. And there's another way of making some regularization. Now we can make a step back to the mini batch definition. So you can, for example, your architecture say that during training, you will use a dropout. So for any mini batch of your, that is the input of your network. So we are looking at one epoch. Okay. In one epoch, you can get, I don't know, 100 mini batches. 100 mini batches of 30 images, let's say. All your, any mini batch that you have as an input will see not the same, can't see the arrow, not the same architecture, but something that is slightly different in a random way. So this is the meaning of the dropout. So for example, if your dropout P rate is equal to 50%, you are saying that for any mini batch that you get as an input, you will delete from your architecture 50% of the neurons. Okay, and in other words, you are just training 50% of the unit of the neuron with that specific mini batch. This means that any mini batch that you get in your epoch, let's say from 1 to, I said 100, your mini batch should will train a different network. Okay, this is something similar to an ensemble. Okay, because back to the machine learning. In machine learning, you can define, for example, a decision tree as a classifier, but maybe you can get 10 decision trees, so make a random forest, for make the same classification. So you get your input as input for all the trees, and then you will get 10 different classifications. And with the voting mechanism, you can decide, for example, that if 8 over 10 say that the input belongs to class 1, this is class 1. Okay, this is an ensemble of classifiers. So it's very similar in this case to an ensemble learning. For different mini batches, of course, at the end of the story, you will get just one network. But this network is trained in a similar way to an ensemble. So because any mini batch sees just one slightly different network. So of course, then you squeeze everything and you get just one network at the end of the story. So these parameters are shared. But it's the way for making some regularization of your network to prevent overfitting. Okay, because if you have that without it,
is prevent overfitting, not to make faster the.
No, just for preventing overfitting. Yeah. Okay, so that's the point. So you want to, if you use all your images and you train with all your images the same model, you will get the best solution for training. But maybe your test will be biased by what you learned during training. In that case, you are not training all the network with your training set, but just few pieces of your network. So you are dividing your network in many sub-networks, let's say, and giving small groups of your inputs to this part of your network to make, at the end of the training, the network more capable of make some generalization. That's the point. So all regularization techniques are intended to get generalization of your network to prevent overfitting. That's the point. And when you decide your architecture, you can add a dropout layer that say, okay, in this specific layer, just for any mini batch that you get, skip the training of 20% of the networks, randomly chosen. Okay. And another way is the early stopping. Let me see. No. In our past lecture, we have seen that once you get your training set, you can, for example, divide the training set in an actual training set and a validation set. Okay, so you train during training, you use your training set for defining the parameters, and then you can use your validation set for, let's say, testing during training your network on something that is completely different from the training set. And then the ratio, typically the ratio between the validation set and training set is about 25%, 30%, 75%, 70%. So once you get you are making your convergence, you are training and you are iterating over the epochs, your error, your loss function should decrease, okay? And the same for your validation set. So the validation set and training set are different, okay, for in our case, in any case. Then, for example, you can stop training once your validation loss starts increasing. So this means that in this specific point, your parameters are going to make the best optimization of the training, but at the same time, the best optimization in your validation set. So if you go on with your iterations with the epochs, you will continue, for example, making the error, the cost function of your training set even better, so lower here. But your validation set will increase the cost, its specific cost. So to prevent, so, and this means that in this case, we are getting some overfitting. So of course, we want to stop the training at the specific epoch. Okay, and this is a criterion of early stopping. So you can define, for example, okay, train my network for, let's say, 200 epochs. But if the validation cost is no longer decreasing for, let's say, 4 epochs or 5 epochs or any parameters you want, stop training. So even if you can get even better results for the cost function in training, that's it, because you can improve, but you will not be able to generalize to the test. And this parameter, 4 epochs, 5 epochs, is called patient. So patience means that you will stop your training for if your validation accuracy or loss is not improved for patience epochs. So this is, let's say, a summary of what we've seen before. So training a neural network, or in any case, an architecture, or in general, involves many hyperparameters. So the learning rate, the drop factor of the learning rate, if you want to use a cosine decay, an exponential decay, a drop factor every 10 epochs of your learning rate, or whatever. The type of the optimizer, stochastic gradient descendant with momentum, the Adam optimizer, or even in the optimizer, the parameters, for example, in stochastic gradient descendant with momentum, you should define your beta value. That could be typically is set to 0.9, but you can set also 0.8, 0.95. There are many hyperparameters that you can set, even in the optimization problem. Or in general, the other hyperparameters could be, for example, the number of layers. How many layers should I have in my network? Or the number of neurons for every single layer. Other parameters could be the batch size, for example. How we can set the batch size? It typically depends on your graphical card. Because, for example, if you want, so if you want to train a network, let's say with images, and then you have 1 million images, it's unfeasible to take 1 million images and put this as input to your graphical card and make in just one time your training. And it's not correct because we have seen that mini batch can help also the optimization problem. Okay, so it's better to divide your training set in some mini batches to get something that is stochastic, and we can get a better training of the network. How we can set this batch size? 64, 32, it depends on your graphic card. Okay. Then the activation functions, we've seen that there are many activation functions that we can use. Also, there are many other parameters, let's say the penalty that you can add for your regularization, the dropout rate, the patience, many hyperparameters. How we can set them? Actually, there's not a recipe. You can, for example, make a grid search and find the best parameters and check any possible value of these hyperparameters. Of course, this will take a lot of time. Or based on your experience, you will set some parameters that for you will work best for the specific problem. So, or with a random search. Now there's a branch of research on the Bayesian hyperparameter optimization. So using some, let's say, prediction of which are the best parameters that can be used for your training. So, but the point is that there are many hyperparameters just for training a network. Okay, and your training could depend on the parameters that you set when you start your training. And this is another point that is important, because when you train multiple classifiers, maybe multiple classifier can work better than just one classifier. So let's remember the no free lunch theorem. There's nothing that works better for all, but maybe you can make many classifiers and then apply, for example, a voting mechanism to get the final classification. And that's the problem of backing. Okay, the classification is based on the average vote that you get from all the classifiers. So you get different networks and then make classification with all the networks and decide for the best for your final class by a voting mechanism. So taking, for example, the mean, the median vote from your classifier. Or boosting. In that case, it's something slightly different, where you train a classifier, then you apply these weights on a training set, and try to define some misclassification cost. For example, if you have that with your first model, you are not able to detect examples of class 5, maybe you can increase the cost, the misclassification cost for class 5. And then, again, in a loop, try to train a new classifier, giving this cost for the misclassification. Then, for example, in the second loop, you will find that examples of class 3 are very hard to be detected. In that case, change the misclassification cost again, till we get the final convergence of your iteration. So you make a tuning of your parameters, changing the misclassification cost that you can get while looking at your results. And that's the boosting of the classifier. Okay, that's a point that we have already discussed in our past lecture. So the cross-validation, where you, instead of making just one separation between the training data and the validation set, and then use the training data for training the network, and then the validation set for testing during training, you will split, you will change the position, the indices of your validation set examples, and then compute a kind of average of your accuracy, and then select for the classifier that make the best performance according to the partition that you get here. Okay, and the batch normalization is another important point, because you know, for example, that, so again, in our networks we have numbers. Okay, so you typically don't want to have some neuron that is managing numbers of high value, of high magnitude. So, because this means that maybe this neuron will be at the top of your decision process with respect to the other one of the same layer. So that means that in any case, for any batch that you get in a layer, you will normalize your output to create something that is on the same level, let's say. Okay, and these are very, very common layers that typically are added within a convolutional neural network, within an architecture. So now we can start with just some brief introduction about the architectures that we can use with deep neural networks. So till now we have only seen something related to multi-layer perception. So this means that we are having a fully connected network that is linked to another fully connected, as long as you want to go deeper within your with your network. But there are many other architecture, many other layers that can be used for your application. For example, architectures. So defining an architecture is up to you. Again, there's not a recipe for designing the best architecture. There are some rules, let's say, but in any case, the architecture depends on many parameters, on many things. First of all, depends on the task. If you are making something for classification or segmentation, for regression, well, classification and regression are quite comparable. Just the last few layers of an architecture can differ, because you, at the end of your network, in one case you want a categorical attribute, class 0. In the other case, you want a number, a real number. For example, you get some input, and then you want the expected depth of your defect. That is a real number. Okay, but the first layers are almost the same, could be almost the same. The last layer should be different, because you don't want to make classification in one case, but in the other case, so you don't want the probability of something that is belonging to a class, of the input, of how an input is belonging to a class. You want a real value, for example, the depth of the defect. Segmentation is completely different, because in segmentation, you are classifying every single pixel of an image. So you start from an image of a resolution, let's say a VGA resolution, 640 by 480 pixels. And then at the end of your segmentation problem, you don't want a number, a categorical attribute. You want another map of 640 by 480 pixels that is filled with the specific categorical attribute for the pixel. So this pixel belongs to class 0, this pixel belongs to class 1. So you are making classification at the pixel scale. So you start with an image, you will end with an image. So you can imagine that the architecture should be completely different to process the data and then create something that has the same size of the input. Or there's another difference. For example, the domain of your input. Your input are still data, so it's something that is fixed. That, for, let's say, in our case, we get the signal. We can process this signal as a whole. So it's something that I have already acquired at the end of my process. And then at the end of the process, I will take all the signal and process it to make my classification. But for example, in speech recognition, you don't have the whole phrase. You have something that is evolving dynamically. In that case, I don't know, you can classify, let's say, a video captioning. You are looking frame by frame to the video and then captioning what is happening for, let's say, 30 frames for 1 second of your video. So this is a time series. It's not something fixed that you have already acquired. Maybe in the first 3 seconds, the caption could be, okay, I'm presenting myself, and then the caption could be, I'm moving and walking away from the room. So it's something that is evolving. In this case, you are facing, for example, time series. Then the architecture is, design the architecture means taking the number of layers that you want in your network, and which kind of layer you want within your network: convolutional layer, pooling layer, batch normalization, activation, and then the topology of the interconnection. So once you get your filters, then you have to make connection between your filters to create to state how the data will flow through your network from the input to the output. So let's start with time series, even if we will make an analysis on something that is fixed, that is our data, our signals that are fixed in, I don't know, 1,500 of samples of temperature. Okay. So typically, when working with time series, you have something that has not let's say, a fixed size, but maybe my way to say a word could be longer than your way or something like that. So you are managing something that is evolving in time. Typically, you will use a recurrent neural network. That, okay, at this, so you will say that when I have one input, let's say x1, x2, x3 are the subscript, the number of the subscript is a time sample. So this is x at time 1, this is x at time 2. So this is an input sequence of your data. So you can, let's say, make some function of your neuron that produce an hidden state. Okay, that is this H. This hidden state is from the time 1 is the input as the input x2 to the second step of your to the second neuron of your network, which is the same before. So you are having just one neuron that is receiving the input now, and the state that we had previously. So in a kind of loop. So once you get all your input states, you can get some output, some prediction. So the prediction is made on, let's say prediction, but also regression, whatever you want to have, is made on the hidden states that you get for some time samples. Let's say for the first 10 time samples, you are acquiring knowledge, and then you get some output. And then you will get output forever for any of your input that you are using for feeding your network. Okay. That's the point of time series. So you are feeding your network, and after some delay, your network will start producing an output for any time instant. And these are used for image captioning, for semantic analysis, machine translations, and so on. Well, just for mentioning it, there are also Can you hear my voice? There was a problem with the network. Can you hear me now? Okay. Go back sharing. So let's start again. This. Okay, so in that case, this is a bidirectional recurrent neural network where the state, the hidden state of your network can propagate not only forward but also backward. So when you have respected your delay, let's say that you get the 10 hidden neurons. So you will start producing after 10 time sample your first output, and then for any timestamp, if time a step, you will produce another new output and so on. You can get backward to improve the capability of your network to store the information. Okay. And then for improving again the let's say storing this information in your network, there's also the possibility to use a long short-term memory. So a memory cell within your network that is storing what is in your what is flowing through your network, and make not only, let's say, a decision about the past 10 time samples, but also taking into account something that is that was predicted many time steps before, depending on on the size of your memory. So this is just a cell of your long short-term memory, but I think that is not of interest here. So for fixed size data, this is something maybe that could be more related to your application context. Typically, when you have fixed size data, questo registra. Okay, again online, right? Maybe yes. So again, in presentation mode. So as I said you before, when you have something that is still, you would probably use convolutional neural networks. Why convolutional neural networks? Convolution can be seen as a filtering operation. If you have ever worked with signal processing, you know that make a convolution in time of a signal means making a product in the frequency domain. Okay, I don't know if this is familiar for you. Making a product in the frequency domain means that you are creating a filter. for example, a low-pass filter has a spectral band that is, let's say, 1 at low frequencies and 0 at high frequencies. And when you make a convolution with this filter, you will produce something that is smoother, okay? So that's the point of convolution. There's another important point, that convolution can move within the signal, because you know that your convolution, your formulation is a summation of something that is a product between two vectors, let's say a one-dimensional convolution, where the kernel is moving on the top of your signal. And when you get your movement, you make a point-by-point multiplication, and then the summation of the result of this multiplication. I think that is something that you already know.
I know just conversion of animating image.
Okay, it's completely the same. Now we'll see how it works for 2D. Okay. So taking images, your convolutional networks, your filters that you will define at the top of your network will extract the features. Then you will take these features and use it for classification. Okay, so you make some convolutional filters, many layers of convolutional filters, and we will see an example. And then at the end of this first part, you will get a feature vector that is automatically defined starting from the data, because these convolutions are empty when you define the architecture, but are populated with numbers when you start training. So you will define the best filters ever that best work, of course, on the training data. Okay, and then once you have these first layers of convolution, for example, you can create a fully connected that is taking as input the result of this sequence of convolutional filters, and then making just the prediction. Is this a koala? Yes or not? So here you will get the probability, the number that this image is of a class of koala, let's say. Now, we will see all these points in the next slides. So, as I told you before, the important thing of this panel is that when you are going deeper in the network, you are increasing the level of your representation. So your first levels should be of low, so your first representation should be of low level, and then the next one should be of higher level, till we get the final vector that is of the highest level. What does it mean of the highest level? That your information is, let's say, concentrated in something that has a lower size, but of the highest informative content that you can get from your input, in this case, image. How we can do that? Using, for example, pooling, using rectifier annealing activation, using many things that you can see now in a few seconds. And then at the end, you can, for example, for a classification task, make your fully connected network with, let's say that you want to classify 10 classes with 10 output neurons, where then at the end you will place your softmax layer to get the final probability. Okay, and that's it. You get the classification. So before going through the architecture, just a few words about the aims that we have behind the use of the convolutional neural network. So in multi-layer perceptron, this is a typical architecture of multi-layer perceptron with just 3 hidden layers. Okay, you can see here that this is fully connected. There's a network of many connections, and probably this is unnecessarily complex. Why we use convolution? So let's say that we want to create a kind of beak detector. So taking an image of a bird, just try to understand where's the beak. So let's say that in this region is enough to understand that there's a beak. Okay, so this is a very dumb example. So if you move this, let's say, beak detector within your image, then you can recognize the same pattern. And that's how convolution works. Now we will see. So you can define your kernel, move your kernel in your image, and make the convolution as for one-dimensional signal. So point by point product and then the summation to get the final output. For example, this is the input matrix. Again, images are matrices and are normalized matrices because we want to start with something that is normalized. Instead of having between 0 and 255, typically we get between 0 and 1 with the standard deviation for each pixel equal to 1. Okay, so the normalization step that we have seen before. So this is the input matrix, and this is a 3D convolutional filter made of zeros and ones. Okay, you will move your convolutional filter in your image, and then make a point-by-point product, the summation, and then return the results here in this point. This is the new, this pink here that now is not completed. This is the new representation of your input image. Let's say that you are defined, for example, this filter. This filter 0, 1, 0, 1, -4, 1, and so on. That has the shape. So this is the input image that is made of one normalized between 0 and 1, and so on. You will take your filter here and then move it through your image till we get the convolved image. So the result of the convolution of this image by this filter is this one. This is a new representation of the same image made by this filter. And this filter was designed to make the edges sharper, okay, brighter than the rest of the image. So this is your new representation. If we go on and go on with this, and we go deeper in the network, we get newer representation that have different meaning, even of higher importance, till we get the final feature vectors. And then these feature vectors could be the input for your classification network, for example, the fully connected. Okay, that's the point. There's another parameter that you should set in your convolutional neural network, which is a stride. The stride is a kind of step. So you, for example, can have this kernel filter, and you can apply this kernel filter with a stride 1. So you make a dot product of this matrix here. So you get this diagonal. So the dot product and then the summation result 3. Okay. Stride equal to 1 means that you are moving your kernel by steps of 1 in your image. Nothing more than this. And then again, make the dot product of these two matrices, of course, of this kernel and this sub-patch of your matrix. And then we'll get here -1, -1, here 1, result -1, the summation. And then go on. With stride equal to 2, you will move with a step of 2. So the next dot product will be this one. So you are also reducing the size of your output with the stride equal to 2. So, for example, in the first layer, you can as in our first example, in the first layer, you can set just one filter and get just one representation of your input image. So as before, let me go back. So one filter, this one, make one representation, but the same input can pass through many other filters. So instead of having just one kernel, I can define any kernel, many kernels, let's say 30 kernels. You will get for the first representation 30 representations from your first time. So it's the same of a number of channels of the image. So an image is made of width by height by number of channels in sides. Okay, let's say 640, 480 by 3, because it is a color image. The first representation that you get with 30 filters will have a size, and now we'll see how we can compute the size of the output of the kernel. Let's say with the same size, but with 30 channels, because we get 30 representation of your image. And this means that we can have, for example, filter number 1 that is working as before, producing a representation. And then, and that's another point, you can see here this diagonal that is working here for these points, but also for these points. This, as you see here, the same region is completely equal. Let's say that this is the beak, for example, because the pattern is the same, produce the same numbers in the representation. If this was a beak detector, you are making the same numbers here. This means that you are actually detecting your beak here and here. So it's independent on the position of your target. Okay, so that's an important point for convolutions. So even if your so beak detector, of course, is something a dummy example, but if your features are in the first in top right corner of your temperature map, or in top left corner of your temperature map, they will produce the same numbers. That means that at the end of your network, your classifier, you should be able to detect, because the input will be actually the same. Okay. Then you can, okay, so this is the map at the previous step. You have another filter, so 2 filters on your first layer. That is also known as a filter bank. That's also the name of your, so when you get many filters, you are creating a filter bank. And you can still process the same input with this other filter and get another representation. So you are increasing the third, let's say in this case, the third dimension. So you are producing 2 different representations of your input image, of your input matrix. This is a feature map. Then this feature map will be the input of another layer of filters, and so on, as long as you're, depending on the depth of your network. And so you get a first layer of feature maps. Then there's another layer that produces another feature map, and so on. So that's a point. Okay, first of all, taking into account, for example, here, the number of filters, the depth of the feature corresponds to the number of the filters. So if you have 30 filters, you will produce a feature map with depth equal to 30. Okay, with 30 channels, let's say. The depth of the architecture is the number of layers that you have in your network. So if you're making 3 convolutions in a row and then 2 fully connected, you are making a network of depth 5. Nothing more than this. Now, in color images, of course, you will define a filter, and every single channel of your color image would see its own filter. Okay, these filters at the start, when you start your training, are filled with random values. And then these numbers, this one, will be the result of your training at the end of your convergence. Okay. Now, there's a parallelism that we can have between convolution layers and fully connected layers. As I told you before, everything started. Okay, let me go back. Very back. Everything started from this. So from the multi-area perceptron. So the idea was, maybe this is too complex. Maybe we can find something that is easier to have a lower number of parameters to be trained, first of all. And then also the architecture that should be easier to be understood. So the point here is that also convolutional layer can be represented as a fully connected layer, but with lower parameters. Let's say this is our input, the same matrix that we get as the input. So filter number one, that is applied in this specific region for the first step of your convolution. And we know that is producing as a result 3. We can take the input image and then unwrap it in a vector. So for example, reading along the rows. 1, 0, 0, 0, 0. I don't know what was here. 0, 1, 0. So we can unwrap it and make it is a vector of 36 elements. Okay. Once you have this vector, you can, so you know that your output should be 3. These are the weights of your fully connected network. And this dark red is this weight. This is the light red is this weight. And then the summation is this one. So it's not fully connected because you are just connecting 9 inputs to produce your output. So first of all, you don't have fully connected. So the number of parameters to be learned, of course, is lower. Then there's another point. If we move with stride equal to 1 to this point, of course, this vector is still the same because the image has not changed. We know that we should have -1. We place it here. And the weights are the same. So weights are shared. Also, in this case, it's not only it's no longer fully connected, but also the weights are the same, are shared. So, and even fewer parameters should be learned. So we are passing from something that is very complex with many weights and biases to something that has a much easier representation. Okay. So, as I told you before, so let's go back. Let's say that you have 30 filters. So you start with something that was a 2D matrix, and now you are producing a 3D matrix of 30 channels. So it's not true that you are decreasing your size. So you are making, okay, you are making a representation that maybe is more informative, but you are creating a lot of parameters, a representation with a very high size. There's an important observation that this is a bird, and even if I subsample this bird, this is still a bird. Do you agree with me? So the point is this one. I will add a pooling layer. A pooling layer is something that may just this. Take the image. This is the representation at the end of your convolution. Okay, let's say one channel of your convolution. The end of one filter at the end, the output of one filter. You group, for example, max pooling with 2 by 2 and stride equal to 2. You group 2 by 2 masks and then you select just the highest value and you put it as an output. So you are decreasing the size, you reduce the dimensionality of the size, it's better. You are decreasing the size, the 2D size of your representation. So you start with something that is 640 by 480, and at the end of your pooling, you will get something that is 320 by 240. Okay, so you are halving completely your resolution. Of course, this mask could be 3 by 3. Your stride could be 2, 1, could be higher. So depending on the pooling that you want to produce in your feature map. And okay, so an example of an architecture. Let's say that you have this, you want to classify this image, this input image, and your classes are living room, bedroom, kitchen, bathroom, or outdoor. Okay, these are 5 classes. You have your convolutional layers, 64 filters, then other 64 filters, and the max pool layer. Then you have 128 filters, other 128 filters, max pooling layer. So you can, of course, once you get an improved, you are going deeper in your network, you will get at the end of your pooling that you are reducing the size of this representation map. Okay. So how many layers can I have in my architecture? Of course, it depends on the size of your data. So you should be very careful with the data size. So let's say that you have an input color image, a VGA resolution. So 640 by 480 by 3. So that's your input image. Then you have 64 filters, okay, that are working on your image. So this means that let's say that all the convolutional layers, for sake of simplicity, all convolutional layers have a 3 by 3 kernel and the stride is equal to 1. Then you have a max pool layer or 2 by 2 pool size, and your stride is equal to 2. So you have 64 filters in your first filter bank. So the learnables are 64 by 9, that is 3 by 3, by 3, because your input has 3 channels. Okay. Then you are making a max pooling, so you are halving your size of your map. So instead of having 640 by 480, you get 320 by 240. Okay, by 64, because now we get 64 representation of the inputs. Then you take this representation here and you get 128 by 64, because you get 64 features in as input, by 9, because your kernel was 3 by 3. Okay, and then so on. At the end of this very, very simple network, you get about 4.5 million learnables. So you should be able, with your data set, to learn 4.5 million parameters. Okay, so the number of pixels should be enough, and of examples, of course, should be enough to make to learn all the learnables that you have in your architecture. Then my first question was, how deep could be my network? Of course, here, this feature map is 40 by 30 by 512. Okay, 512, because I have 512 filters in the last layer. And then I make at the end the max pooling. So this is of a very low size. Maybe I can add, I don't know, other 2 layers, but then I can get some at the end. If I add other 10 max pooling layers, maybe this is equal to 1, and I cannot make another max pooling. Okay, so you should take care of the data. You can go deeper as you want, but sizes should be reasonable. So you will not have 1 by 1 by 1,000 channels in your at the end of your feature map, your last feature map. And then once you get this feature map, you can flatten the vector and make a vector, a one-dimensional vector of 614,400 entries, which is equal to 40 by 30 by 512. Okay, that's the last vector. That is the input of your, let's say, fully connected layer. And then at the end, you get 5 outputs that are the probabilities of your input to belong to a specific class. Okay. So there are many examples of convolutional neural networks that you can find in the literature. Of course, I will go very fastly through the most, let's say, important, but it's just a bird eye view of all the literature. So in the next slide, I will use this legend. So this is the input of an image of size h by w by c. C is the number of channels, and this is the spatial resolution. Then a convolution with the filter size f by f, max pooling with the pool size n by n, or average pooling, or global average pooling. Then fully connected layer at the end with D neurons. D neurons means that I will predict among D classes. Then this notation means that there's a subsequence of n equal blocks. And then this is the hyperbolic tangent function, activation function. This symbol here means that the activation function is the rectified linear unit, softmax, or there's a local response normalization or the batch normalization. So we are getting together all the things that we have seen before. Then inception, we will see in inception v1, what is it? The same for convolutional block in ResNet 50, the identity block in ResNet 50. Then concat means that I'm concatenating the results of the convolutions. Add means that I'm adding the results of the convolutional layers. Okay. The very first convolutional neural network proposed. Okay, so there was, let's say, 13, 12 years ago, there was a challenge in the scientific, between scientific groups working on convolutional neural networks. This challenge was the classification of images from a dataset that was the ImageNet dataset made of, I cannot remember how many images, but with 1,000 classes. So in this challenge, all the groups proposed, within this challenge, all the groups proposed their own architecture trained on this ImageNet dataset, and then published their results for benchmarking with the other networks. Before this challenge, the first dataset that was used was made of 32 by 32 images of digits, so of simple digits. So the number of classes was equal to 10, and that's why at the end of my fully connected, I have 10 neuron. So because I want 10 classes. And this S means a softmax layer that is used for classification. This was the LeNet 5 network. That was probably the first presented in the literature for this specific task of recognizing digits in the range between 0 and 9, of course, and written digits. The input was the image, black and white image, grayscale image, 32 by 32 by 1, the size of the image. Then a convolution with a 5 by 5 kernel, with the activation function, the parabolic tangent, and then the average pooling 2 by 2, another convolution the same as before, another average pooling, and then 3 fully connected. The first two with an parabolic tangent activation function, and then for the last one, the softmax, because we want the classification. This was the first study proposed. So where the architecture was made, was designed to solve this, let's say, easy problem. Then, I told you before, there was this ImageNet dataset, and there were a very impressive challenge between groups working on convolutional network or on deep neural network to make the best architecture for the classification of these 1,000 classes. Okay. In that case, these AlexNet network takes as input images, colored images of 224 by 224 in size by 3, because these are RGB images. And then there's convolution, max pooling, then 3 convolutions, max pooling, and 3 layers of fully connected, where the last one layer as also as softmax activation, because we want the probability. And then we get 1,000 because we are classifying 1,000 classes. Okay, this was one of the first presented for this specific problem of classifying the images of the ImageNet dataset. Then VGG19. Why I'm showing you this architecture? Because these are in Matlab, for example, these are known. These are, you can import these networks in Matlab and use it as a pre-trained network, and then try to adjust, to tune your the weights that are in these filter banks to match your problem, to get the best results with your problem. Okay, you just need to use transfer learning. So as you see, in time, we are seeing something that was proposed in the, I don't know when, maybe in 2014, 2013. I cannot remember when. As time evolves, the number of layers increases because there were much more capabilities in computing, training the networks. So they, in this, the authors of this architecture propose, for example, 2 times this convolution, max pooling, convolution, then max pooling with really rectifier and unit activation function by 3 times. And then again, 3 classification, 3 fully connected. And then at the end, 1,000 outputs for classifying 1,000 classes. Inception make use of this inception layer where the input is splitted, is divided in many branches with convolution of 1 by 1. What is a convolution by 1 by 1? Means that you are make a product with just one element on your, so your kernel is a scalar. So you are just multiplying your image, your representation map, your feature map by an element. And then you concatenate all your results to get a new representation, a concatenation of representation. Then there was another point. The authors added 2 branches. These 2 branches are not used in testing. These are used only in training, during training. So these are working just for having a cost function that is not calculated here at this point. That is the final branch of your actual network, but takes into account also what is out from these two branches before the tree inceptions and between the tree inception and this other inception layer. This was another way to make another training on the network. And then the ResNet 50. And there's here a convolutional block made, as you can see here, by convolution one by one with batch normalization, a rectified linear unit. And then there's an addition because of your maps. And then the identity that is made by an addition of the same input by the result of these three convolutions. Okay, made few times, 2 times here, 3 times here, 5 times here, 2 times here, and then the final fully connected with 1,000 neurons to get the representation of this, the classification among the 1,000 classes. As I told you before, it's important to understand the meaning of transfer learning. Let's say that you want to use, for example, the AlexNet. You have a problem of classification. You want to classify an image and say that your image is an image with something that has a defect inside. Just classification of your image. Okay, nothing more than this. Maybe you will say, okay, let me try to use the AlexNet. And instead of making a classification among dog, cat, car, and duck, and whatever, I will make a classification between two classes, defective, non-defective. Okay, but starting my training, my new training, not from the scratch, so randomly picking the weights, but using the same weights of the AlexNet that has been trained on millions of images, even if the final task, the task that was used for that mostly the final aim was to make a classification among cat, dog, ducks, and any other animal of the farm. So the idea is take the last layers. Let me go to the AlexNet. You have this one. You make this layer, you remove this, and replace it by fully connected with just 2 outputs, okay? 2 neurons instead of 1,000, because you want to classify just defect, non-defect, okay? Your input must match the size of the input of the AlexNet, of course. So if your image has I don't know, resolution of 2,500 by 1,080 and 800 pixels, you should resize your image and make this image as input to your AlexNet. Should match the same size, 224 by 224 by 3. Okay, that's a focal point. Or maybe better, if your image has a good resolution and you don't want to, and your resolution has a meaning, so my pixel is 1 millimeter projected on your target, and you don't want to lose this good resolution, maybe you can take your image and divide it in sub-blocks, and then take these sub-blocks as input for your AlexNet. And then say, okay, my transfer learning, I can do my transfer learning like this. The last layer has a learning rate high. This alpha that we told, that we have seen before. My learning rate of this layer is very high, and the learning rate for the other layers is low. So I'm saying to my network, okay, tune your parameters, your theta parameters here on the first layers slowly, because you should take your knowledge. You should keep your knowledge that you have already acquired, training cats, dog, and whatever, and just making a learning rate that is very high on the last layer, where actually you make your classification that is different from cat, dog, and so on. And then retrain your network, not starting from random weights, but starting from the weights of your AlexNet, or the AlexNet that is available even on Matlab, the same with the VGG19, RESTnet, with many other networks. Then retrain this network, taking the first weights slightly constant, because your learning rate is very low, but taking the learning rate of the last layers high, to make the prediction with your classes that are specific of your domain. That's the point of transfer learning. In these cases, we have talked about just convolutional neural networks for classification. Okay, but if we go back, there's a problem of segmentation, for example, where so you start in a classification problem, you get an image, and then you get a classification. Defect or not defect. Okay, that's a classification. All the pixels of your image has the same meaning. In a segmentation problem, you will create another map where every single pixel is let's say, is labeled with the class of with the predicted class among the possible classes that you get in your training set. So to get this result, you should make a deconvolution. So you get a first, let me see here, a first network, a first convolutional network that is taking your dog and is with pooling, convolution, and so on, is reducing the size. Then you have something that is flattened, okay, that is your feature vector, where the information that this image is a dog is completely concentrated. So this is a feature vector. So let's say that this feature vector is full of DOG, dog. So here at this level, you are encoding all the information of your image and say, okay, this is a dog. Then you use the convolutional network that works in reverse order as the convolutional network to get the same image size at the end, where the pixels are black, means that it's background, and purple means that this is a dog. In this specific point, you get a dog. And this is an encoder-decoder architecture. The convolutional network is known as a backbone. This backbone could be, for example, the VGG19. This should be the AlexNet. And then on the convolutional network, you make a kind of mirror, let's say, even if it's completely inappropriate, of your data to get the input size and make the segmentation. Okay. For example, let's say that here you get an image of with some defect inside. You can make an encoder-decoder architecture to get this perfect segmentation of your defect within your input image. Okay, so you create an encoder-decoder architecture with a backbone that is the VGG19, the AlexNet, the GoogleNet, the DeepLab, any other backbone, the same as that we've seen before, made for classification to get a feature vector, and then the convolution to get at the end of your architecture the input size with the perfect segmentation pixel by pixel, classification pixel by pixel of your input image. That's the point of your encoder-decoder. So you make your representation of even more channels as you go deeper with your architecture, but with lower size in space, and then upscale everything till we get the final representation of 224, the same size of your AlexNet, for example, because the input image should be of the same size, of course, of your backbone, and then by C, which is the number of classes that you want to segment, instead, of course, 3, that is the color image. Okay. And there are many encoder-decoder architecture. So the backbone is the convolutional part of your encoder-decoder architecture, but there are many if you see it as a whole, there are many possible architecture. For example, the Deep Lab. The Deep Lab as a specific introduces for the authors of these Deep Lab networks introduces for the first time the concept of outrouse convolution. So in our case, convolution was a fixed kernel 3 by 3 that is moving on the image. In outrouse convolution, this kernel, instead of, well, is even equal in size to a 3 by 3, but works on larger area. So it's easier to make a sketch here.
What's the name of this?
Outrouse convolutions.
Oh.
Outrouse. If it opens. So in convolutions, let's say that you have a 3 by 3 kernel, and you are applying this kernel on your image like this. In outrouse convolution, you have a kernel of the same size, but if this your image, maybe it's not the best image that I can do for you. You are applying your convolution here, here, and here, and then here, here, here. So you are taking your kernel, let's say that you are enlarging the area of application of your kernel. Okay, the number of unknowns here is even equal to 9. Okay, but they apply in a different way. Instead of in this group, these are, let's say, spread on your image. Okay. So why they did like this? Because in segmentation, maybe you are defining something that is a 3 by 3 kernel, but for segmenting a point, maybe you want to take into account the information of many more neighbors. Okay, not just of the 3 by 3 neighbors, but maybe from larger areas. Okay, but you want to keep this number 9 as low as possible, because if you define, so in this case you are covering an area of 5 by 5 elements. So the number of learnables should be equal to 25. This is much higher than 9, of course. And that's the point. Instead of grouping the kernels, it applies in a spreader, let's say, way. Okay. Now, so these are architectures for segmentation. Now, the last point of this lecture is to open Matlab and just have a quick example of training a convolutional neural network on our dataset. Our dataset is still this one. So we are inspecting our calibrated plate made of glass fiber reinforced polymer. This is the ground truth. Everything is completely known. And we have already divided a training set and a test set. Okay. the same of our previous lecture. So let's go back here. Of course, this Matlab code is available. All the data are available. You can replicate it at home. And if you have questions, you can text me a message and we will see together.
Teams.
Not on Teams, on the website. Okay, I can write on Teams my website, and then there are other lectures, presentation, PowerPoints, materials, everything is available. Okay, so the point is that we are loading here, just loading the input sequence, thermal sequence, and then the ground truth, just opening the labels. So let me do this for you. And then, as we have already done in our previous lecture, I'm selecting the cooling regime. So instead of working on the warming up and the cooling, I just take the decay of the temperature. How can I do that? Taking the maximum value of the input data along the third dimension, which is the time. This is the position of the maximum, where is the perfect time sample where I switch off my lamps. Then making a mean, an average of all the time samples where the lamps are switched off. Casting it to the sale to the higher, casting it to the higher integer, and then selecting those time samples from the position of the maximum of the temperature to the end of my signal. Okay. Now, these are the lines of the codes for removing the discontinuities, because if I plot my T pool in, let's say, in position 100 by 100 by everything, and squeeze it to make it a vector. I will plot it. And if you see here, there are two discontinuities that are probably due to somebody that is coming, that is a reflection of the temperature of a body that was working on in front of the sample. I want to remove these discontinuities, and then assuming that for 30 samples, this profile has a decay that is linear, I'm selecting these discontinuities. I know that just looking at the images, that these discontinuities are placed at a time sample of 422 and a time sample of 1324. Okay. Then I will select this discontinuity and then compute the temperature decay before the discontinuity, 30 samples before the discontinuity, compute the difference, the first derivative of my 30 samples, and then the average decay. I'm just assuming that this slope, that this completely linear, and thus the average is representing my slope. Okay. Then I will add it to remove my discontinuity at the end. It's the same that we have already seen. Okay, the discontinuity was not defined. Okay, I will have at the end this vector here of, and we can plot it. instead of tcool, taking tcool that, sorry, okay. Okay, I'm not plotting the same, actually the same point, the same profile here, but there are no discontinuities, as you can see. If I plot, for example, let me check. 40,000. So maybe here there was a discontinuity, but now there's no discontinuity because I remove everything by my first assumption. Now, temperature normalization. As I told you before, maybe it's better instead of using the temperature as it is, so between 32 degrees and 24 degrees, taking it normalized between 0 and 1. So just normalizing by subtracting the minimum and dividing everything by the difference between the maximum and the minimum of temperature. Nothing more than this. Then, as we want to use the temperature contrast, that is the difference between the expected, between what you measured from your surface temperature and the expected surface temperature that you expect from a sound region, a region without any defect. Okay, we can compute this, the contribution of your source, because as I told you in the first, in the previous lecture, we can say that any defect that you have in your image should be of small size, because you are testing something that probably is out of a good process. Okay, so your defect should be very, very small if compared to the whole image. And if we take the surface, the temperature, the surface temperature of all your image, and we make, for example, a median temperature decay, maybe this should be equal to the sound, to the temperature decay that you should have with a sound under sound condition of a sound material. Okay, so starting from the assumption that is valid, that your process is good enough to have small defects, comparing this defect, the size of this defect, with your background. Then we can compute the contrast of temperature. And these are the available data in terms of temperature contrast versus time, okay, in the cooling regime. So we are just looking at how the temperature decay in time. I just picked the exact position of the center of the defects of the two classes that we are considering, surface defect and in-depth defect. So these are, okay, I know that there are many cars, but for example, this blue curve here is from an in-depth defect here, or from a surface defect, while this cyan here is from an in-depth defect. Okay, so this is a normal, the temperature contrast out of different regions of defects, surface defects or in-depth defects. Of course, the contrast in an homogeneous region is equal to 0 everywhere, because we are making the difference between what I expect from a sound region from the expected temperature behavior. So this will be flat and equal to 0. Okay. So this is the starting point of our past lecture, or maybe not, because there's another point. So I divided my data set into a training set and a test set. So I just pick the central line, the center of column of defects, and say that this central line of defects is a test set, while the remaining part is of a training set. Okay, so let me draw it for you. So let's say that this is my ground truth. There are the defects here, like this. Okay, I'm taking this region apart from test for testing, and these other regions on the side for training. Okay, I will use this pixel for training and this one for testing my network. The problem is that if I do just like this, I will have like this. I'm just dividing the test and training sets. I have that if we look at the ground truth in of the training set, the ground truth is almost 0 everywhere, where 0 means, you see here, means background. Okay. So this is an unbalanced data set. There are many ways to contrast unbalancing of data sets, but maybe the easiest is taking my data set and say, okay, instead of taking all the points of the background, I just pick, select randomly fewer number of points from the background to get comparable the size of the data set of the classes of your set of classes. Okay. And I will take just 10 times here 10 times examples from class 0, then let me say in another word. I will take, okay, just to read the example, sorry. This is a number example of class 1, okay. I can take 652 examples from class 0 and make randomly sorted from the whole data set, the whole training set, okay. But maybe it's not good. Why it is not good? Because your background, as I told you before, should be with an higher cardinality than your defective regions. So if you are giving the same perfectly balanced data set, and you are giving just 652 examples of class 0, 652 examples of class 1, and the same for class 2, maybe you're saying to your network that all the classes can, all the cases could happen with the same frequency. But no, that's not the truth. So maybe it's better to give more examples of the background just to make, to let the network know that your number of examples of the background, or that your final prediction should be driven, should be biased by a background decision, okay, even instead of the same importance for background class 1 and class 2. And that's why I'm just picking 10 times this number. So I will pick 6,500 examples from class 0, and then 652, and 652 from class 1 and class 2. That is the whole number of examples that I have in my training set. Then I'm balancing my training set like this. And finally, I will split the training set into an actual training set and the validation set. So my validation set should be in this case, of 25% of the training set. So while training the network, I will use 25% of the examples for testing during training. Okay, this validation set is taken from the examples of the training set. Okay, not from the test set. The test set is as it is, as I picked initially. And here, with CV partition, I'm dividing the validation set and the training set. Okay. Now, Matlab needs this. I'm doing nothing, really nothing here in this cell. I'm just reshaping my my data to let Matlab work with the neural network, okay, with the convolutional neural network. I'm rewriting my data to be acceptable by Matlab for training, nothing more than this. Now, let's decide now the hyperparameters of the network, and then the architecture of the network that I want to use for my classification problem, for the classification of every single signal in temperature that I have from my data set. So the parameters, first of all, I will decide for the mini batch size. Here I'm just taking, okay, my laptop is able to manage up to 64 inputs altogether in my mini batch size. So I will take the number of all the possible mini batch size between 1 and 64 and check for the one that makes that is divisible, how can I say, without any rest. How can I say in English? Help me, I'm tired. Il minimo comune divisore. Cioè io, okay, the problem is that I have that my number of training example is equal to 5,800, okay? And I want to divide it by batch sizes to get, I don't know, 100 batch sizes, 100 mini batches of size, in that case, 58.68 elements. So the point is that one. I will take, sorry, starts from here. The number of iterations per epoch should be an integer, and is equal to 163. And if I divide the number of training example by this number of iterations per epoch, I will get the size of my mini batch. Okay, they should be all integers. So that's the point of, I don't know how can I say in English, maximum divisor. My mini batch size is equal to 36. Okay, I can manage up to 64, but to have this number of iterations per epoch equal to an integer, my mini batch size is equal to 36. Hope that you understand me. So these are all the trading options that I can set. Maybe there are other training options to be set in Matlab. So you have, for example, the learning rate drop factor. So every epoch, I will divide, so because this is 0.5, I will divide my initial learning rate by 2. Okay. And then so on until I reach the final convergence. My maximum number of epochs is equal to 50. But I fix my validation patience to 4. So I will end my training once my validation cost for 5 epochs in a row is not going to increase. Okay. I will make my mini best size equal to mini best size, that is 36. All my processing will be on a GPU. And now I'm defining my layers here. So these are the layers of my convolutional neural network. So there's a sequence input layer, then a convolutional one-dimensional layer, one-dimensional because I'm working with signals, with a kernel size of a number of filters of 64 filters with a kernel size of 32. Okay, so my kernel should be a vector of 32 entries, and I would get a filter bank of 64 filters. Then a batch normalization layer, a rectifier linear unit layer, and a max pooling in one dimension, of course, of size 2, of pool size equal to 2, and then the stride equal to 2. Okay, I'm just write down what we have defined previously in our presentation. Then again, another convolutional layer. Okay, for example, like this. I can run this cell, and then I can open the deep network designer. Well, here I'm defining my network, writing down the code. So convolutional layer, batch normalization layer, but actually you can also use an app, which is this deep neural network, deep network designer. I can import my architecture from the workspace like this, and here you will see in a while the layers that I defined in my code. Okay, so if I pick, for example, this layer, this is a segmentation input with a minimum length that is actually equal to the expected length of my signals. Okay, because I know this, the number of time samples of my temperature capture. Then there's the convolution one-dimensional layer with the filter size with 32 filters and the kernel 64. I made a mistake before. And I can also analyze my network, and then I can have this information. These are the sizes of all the representation of the activation function that I get in any of these layer. For example, at the end of my last rectifier linear unit, I will get a representation of my input signal that was of 1,570 time samples, that is reduced to 282 samples and 32 channels. Okay, so I can, in this case, I place here a max global pooling one dimension, so I just pick the maximum of time for all the 32 signals that I get in my flow of data, and I get a final feature vector of 32 features. Okay, where there's all the information about the signals that I get in my first layers, input of my first layer. Okay, so instead of having a signal of 1,570 time samples, I get 32 features. Nothing more than this, a vector of 32 features. That is now as input of my fully connected. At the end of my fully connected, I get 3 classes, because of course I get my class 0, class 1, and class 2 that are background, surface defect, and in-depth defect. I can then close that. So this is just for making a visual representation of your layers. Once you have define your architecture, then you can train your network just with this line of code. And you can start your training. That will take, I don't know, 15 minutes, 30 minutes, 1 week, depends on your data. Of course, I will stop it, but just to show you, not busy. Okay. So this is just to show you the concept of convergence in this case. So I started my training. Now, okay, it's recording. It's sharing the screen and making it's not easy. So the thing is that one. So this is the accuracy that you get in your validation, in your training set. So we are giving batch size, mini batches to your network. And anytime you get a mini batch, your accuracy, your loss is going to decrease, and then your accuracy is going to be higher. Okay. Then at the end of your epoch, when you completed all the mini batches, then you can compute your validation accuracy and your validation loss and say, okay, my validation loss for the past 4, because my patience was 4, for the last 4 epochs was higher or lower. If it was lower, then I stop training. Okay, I set a maximum number of epochs of 50, if I can remember well. Maybe I can, with the criterion of the early stopping, based on the patients, maybe it would end in at epoch 20. I don't know when. But you can see here, this is the typical progress of some network that is training, let's say, well, because my accuracy is going to be close to 100%, and my loss is decaying. Okay. Your loss can decay, but your accuracy can, for example, reach 60%. And then here you can have a plateau. In that case, your network is not enough smart, is not enough complex to create a model that makes your accuracy close to 100%. Okay. So you need to improve your architecture to add more layers or improve the number of filters, increase the number of filters, increase the size of your kernel. Maybe you just have to tune these parameters for your network. And until you get that your accuracy is higher than 80%, 85%, 90%, depends on your domain. In my case, I can get very good results. Okay, I will stop it and load the results that I get. If it stops, I will load this result with this specific network. It's busy, it's still stopping. Okay.
What's the name of the network that we use in this case?
That's not the name. This was made by me. Oh. I just placed.
So it's not a transfer learning?
No, not transfer learning. But in any case, let me stop it. Okay. Perfect. If I open this up here, on this deep network designer, the start wizard is saying do you want to use an architecture that you already done in your, let me open. in your workspace, you want to create something blank and then make your, or you want to import some of this. Here, there are many networks that you can use. You can also import other networks, the AlexNet or whatever you want, the ResNet 50 that we discussed before. So you can, of course, I need to install it, so download the networks and so on. And then you can, once you get this, you have installed it, you just go. Let me import this one that is already available. You just go here. And then change, for example, the size. Instead of 1000, that is the up to size of the AlexNet, change it in 2, because you want to make a classification between a defect or non-defect. Okay, and then, so here there are the L2 factor. So there are all those regularization terms that we have already discussed. So everything is now here. So in practice. And then, okay, once you define it, you can export your network like this to workspace, and then work with all the layers and set different learning rate for the layers, and make transfer learning, as I told you before, with high learning rate for the last layers, and then a low learning rate for the first one. Okay, that should be untouched from your data set, because you want to take advantage of what you have already learned from another data set. Now, okay. I have already trained a network, so I'm loading it, and then plot the final training accuracy, displaying the final training accuracy on making the predictions here. So with this function classify using my net, and making a prediction on the whole training set. So including also the data from that were skipped to make the training set balanced. Okay. Now it's taking a few seconds because this training set was I don't want to say huge because these are very small data sets, but it will take some time of my laptop. And display the training accuracy if possible. Just a few seconds. It is classifying. Okay. Maybe I should save also this final result. It's taking time, this classify. Maybe it was better to save also the result of this classify function. It's taking a lot. while we're waiting for this result, because it's busy here, you see here that it's working. Then the same, I will make the same classification on the test set. Okay, my training accuracy is 99.26% here. You see here. Okay. So accuracy means the number of correct predictions divided by the whole number of examples of my training set in this case. Then the same, I can do the same also for the test set, and it should take not so long, hopefully. And compute also the metrics in terms of accuracy, balanced accuracy, recall, precision, and intersection over union for the classes. And finally, plot my prediction and compare it with the expected ground truth. For a network that is very, very easy, made of just 16 layers. So why these are commented here? Because if I uncomment, I will add another convolutional layer, another batch normalization layer, a rectified linear unit, and max pooling. So I'm adding another convolutional layer to my network. So I'm improving the complexity of my network. Because although my test accuracy here is 99.44%, which is very, very high. If I see here, my class 2 has a very low recall, 23%, where recall in applications where safety is mandatory. So you should have a recall as high as possible. That means that if I plot my predictions, so you get that this class here, well, is actually well predicted. So you see here that there are a few points where this is yellow. But maybe adding another layer, another convolutional layer, you can improve the capability of your network to recognize the effects of that class. Okay. And here I'm just reshaping the prediction made on the signal, the temporal signals of the test set, and making it in a kind, reshaping it a kind of segmentation. Okay. Then at the end, we will see here that with 16 layers, that is very low number of layers, are able to detect here these points of the class 2. Increasing the number of layers, and you have the code, you can do this at home. You will see better results here, and you can improve you can increase your recall metrics. Okay, that is very important for those quality control that should face safety requirements, for example, in aeronautics. So even in any case you have a defect, you should be able to detect it for safety reasons, of course. And it's better to get false positive than false negatives. That's the point. Okay, so do you have any question about this? The code. I know that we have seen it very, very, very fast, but this was just to give you some idea of how you can process your own data with some architecture made by you, tailored by you, or importing with transfer learning using the deep network designer of Matlab. That is, I think, the easiest way to start with this problem. Sorry for being late, but there was that problem of the network. So, is there any question from you at home?
No, thank you, Professor.
Okay, so the next lecture will be the last one, and I hope you can be here in you can attend it in person. If you be here, I will give you a present. Okay. So thank you. What's the optimal recall value in comparison with precision accuracy? Okay, so for well, recall can be, of course, between 0 and 1. That's the point. And the same as precision and accuracy. The best should be take these recall values as high as possible, means 60%, 70%, because, for example, in this case, you get that the recall is 23%, but even if it's very, very low, you actually have some points here that is giving you an information that maybe there's something here inside. Okay, so you know that there's something here, but with a low recall. Improving will give you more evidence of this of the shape, of the round shape, and 60%, 70%, 75% will be an acceptable value. Of course, any value over this 70%, 75% is even better. Okay, so see you on Friday, and thank God, should be Friday. It will be Friday. See you. Bye.